hang up and try again.
One of the most important problems in mathematics, not necessarily in computer science, is the Fibonacci. The Fibonacci is the sequence of addition of consecutive numbers to a given number. It's not like factorial. Factorial was the product, but in Fibonacci, basically you start adding with 1. That's the very first number, and then you add 1. So 1 plus 1 is, it will give you 2. And then you add the 2 consecutive value, which is 1 plus 2, that will give you 3. By adding the last 2 consecutive values, 2 plus 3 will give you 5. 5 plus 3 will give you 8, and so on. This will generate 8, and then 13, and then 21, and so on, right? So that will give you this whole Fibonacci series. Fibonacci series are very well known in computer science, data sciences, and of course in mathematics. So the whole idea here is to come out with a program that basically solves this Fibonacci series. And we need to recognize, of course, what we call the base case, and we need to recognize the recursive case. So the base case, if you remember, is when we need to stop. The recursive case is what makes us go forward again and again and again. That's how we move through the recursive. We need a value n, so we're going to start writing the program here. Public static, we're going to return back an int representing the sum of the Fibonacci. I call it Fib for Fibonacci, and I'm going to need the number n. So the idea here, ladies and gentlemen, I want you to pay attention how elegant this solution it can be. The first thing is that we need to establish our base case, when we need to finish. So one of the things that we need to understand is that because this is addition, we perform addition in all of these numbers. Similar as the factorial, we can go in decreasing order. Why decreasing order? Because the user is going to give us n. And we can either go all the way to that value n, or we can just subtract one value and then just add it all the way to 1. In other words, if n happens to be 1, we will return 1. That is our very first case. What do you mean with the very first case? Because it might happen that we arrive to 0, and maybe this will be better if we just have the if statement. If n is equals to 0, there is nothing to return. So return the 0. So those are the two only the base case. If n is equal to 0, return the 0. If n is equal to 1, return 1. So we can stay with this formalization. We just need to incorporate the definition is 0 plus, because 0 plus 1 will give us 1. Now 1 plus 1 will give us 2. 1 plus 2 will give us 3, and so on. So if it happens to be that n is equal to the 0, then we just return 0. But if it happens to be n equals to 1, we return 1. How about otherwise? Well, otherwise will mean the following. Will mean that we need to return, the return statement will involve to add the consecutive 2 values, which will be n minus 1 plus the Fibonacci of n minus 2. Yeah, that's the definition of Fibonacci. Why n minus 1 and why n minus 2? So remember that we're gonna start with certain number, for example, 5. If it's 5, we need to calculate 5 minus 1, which is 4, plus Fibonacci of 5 minus 2, which is 3. And 4 plus 3, which will be these two guys, will give us Fibonacci of n. So every time we have the two different calls, one from n minus 1, one from n minus 2, you will have to divide the computations. Now, notice how elegant are the base cases, because if n is equals to 0, there's no problem. We just return the 0. If n equals to 1, there's no problem. Just return the 1. But the problem is that if it's not 0, if it's not 1, then we need to make this computation, which means that we need to subtract 1 from n, and we need to subtract 2 from n, and then add them recursively. This is called binary recursion. Why binary? Because you're going to have a method call in the left-hand side with Fibonacci of n minus 1, and you're going to have another call to Fibonacci to the right of n minus 2. Ladies and gentlemen, this will compute the Fibonacci series, the Fibonacci numbers. The problem here is that this will bring with a price, and this is called complexity space analysis. We're going to talk about those complexities in the next chapters, but recursion will take an important role in the design of algorithms and in the design of the programming or in the code that you provide as a solution for certain problems. The reason why I'm telling you this price is because from now on, when you design a program, when you design a piece of code, you need to think into consideration what will be the complexity analysis, how long it's going to take in order to solve this problem. And I will illustrate this in a different video, how expensive recursion can be. So let's save, compile, and run this program and see what happens. So as we can see right now, what is the Fibonacci of 5? So Fibonacci of 5, remember that this is Fibonacci of 0 is 0, Fibonacci of 1 is 1, Fibonacci of 2 is 1, Fibonacci of 3 is 2, Fibonacci of 4 is 3, Fibonacci of 5 is 5. So we can demonstrate this with a loop to see how we can generate those Fibonacci. Shall we? Let's generate basically from 0 all the way to 10. And I'm gonna migrate this piece of code into my loop so you guys can see the actual table of what we're trying to do. So what I'm just doing here is just for the purpose of display what exactly we want to print. Let's call the first 10 Fibonacci's numbers. And here I'm gonna say n, and then I'm going to say the Fibonacci of n. So you can understand what we're trying to do here. Here are the answer for the very first 10 iterations of recursion of Fibonacci. So we're generating from n equals to 0 all the way to n equals to 10. Then we see in the right hand side of this table how we actually generate those Fibonacci. Remember that Fibonacci is calculated by the previous two values. That's how we generate the actual value. For example, n equals to 10 is 55 because you add 34 plus 21. N equals to 9 is 34 because you added 21 plus 13, and so on. So here you can see a very elegant solution for the Fibonacci from line 14 to line 21 when we establish the first two base cases, which means that here's when we need to complete, when we need to finish, when we need to stop, the base case. And the recursive case is when you self-call, your self-invocation of the actual method Fibonacci with n equals to -1 plus Fibonacci of n equals to -2. In a different video, I'm going to show you how long it takes this, what is the complexity analysis, because now we need to worry about designing an effective piece of code, a piece of software that basically helps you to speed up your machine.